Today, we are diving into 101 things I learned in engineering school to really get a handle on the hidden logic that pretty much shapes our entire world. We're going to talk about the invisible forces that are at play in, everything from massive bridges to your coffee mug. We'll uncover the secret personalities of the materials we build with and, see why failure is often an engineer's absolute greatest teacher. So, let's jump in.
Right off the bat, the book points out this huge disconnect. Engineers think their jobs are fascinating, but to most of us on the outside, it just looks like a bunch of repetitive math and really strict rules. So what's the real story here? Which one is it?
Is it really just about crunching numbers and following a formula? Well, the book makes a great point. That's like saying cooking is just about measuring ingredients. The real magic, the actual heart of engineering, is something totally different.
And this right here, this is what it's truly all about. The core of engineering isn't calculation. It's this creative problem-solving loop. You find a problem, you brainstorm ideas, you build something, you test it, and inevitably, you find out where it fails. Then you go back, you troubleshoot, you refine it, and you start the whole cycle over again. The math? That's just one tool in a much, much bigger and way more creative process.
Okay, so where does an engineer even begin? Well, before you can solve a problem, you have to learn to see the world in a completely new way. You have to be able to see all the invisible pushes and pulls that are constantly at work on everything around us.
I mean, think about it. Literally everything you can see is in a constant tug of war with forces you can't. You've got the weight of snow pushing down on a roof, the insane pressure of water squeezing a submarine, or just the wind pushing against a skyscraper. An engineer's job is basically to manage that relentless battle.
And this is where engineers get super specific. But stick with me, it's actually pretty simple. Think about stretching a rubber band. The force is just you pulling on it. The stress is the tension inside the rubber that's fighting back against your pull. And the strain, that's just how much the rubber band actually stretches. See? They're all connected, but they describe three totally different parts of what's going on.
And you know what? At the most basic level, it all just boils down to this: tension and compression. Things are either being pulled apart or they're being squashed. The giant cables on a bridge, they're in tension. The huge columns holding it all up, they're in compression. It's really the fundamental push and pull of the entire physical world.
All right, so knowing about the forces is only half the battle. You also have to understand your materials, because every single material responds to that push and pull in its own unique way. You could almost say they each have their own personality.
Check this out. This is a stress-strain curve, and it's basically a personality test for a material. The one on the left is super stiff and strong, but it'll snap without any warning. The one on the right is less stiff, but it can absorb way more energy before it fails. It's tougher. Now, neither one is better. It all depends on the specific problem you're trying to solve.
Here's the core difference in the simplest terms: brittle versus ductile. A brittle material, like a piece of chalk, just snaps. No warning. A ductile material, like taffy, is going to stretch and deform and give you a really clear sign that, hey, it's about to fail. So an engineer has to pick the right personality for the right job.
But, and this is a big but, materials don't exist in a vacuum. They interact with each other, and sometimes that interaction is disastrous. Let me tell you the cautionary tale of the ship called the Sea Call. It was built back in 1915, and it had a hull made of this stuff called Monel, a super strong corrosion-proof metal. I mean, this ship was literally designed to last forever. But it was a complete, catastrophic failure. The ship had to be scrapped after just 6 weeks. And here's the wild part. The super strong Monel hull was totally fine. The problem was that when you put it in salt water, its chemical interaction with the ship's steel frame made the frame corrode at this unbelievable rate. The two materials literally ate each other.
And that is such a critical lesson. It's not about finding the strongest or the hardest or the most advanced material. True engineering is about the entire system. It's about understanding how all the different pieces are going to work or fight together out in the real world.
Which brings us to an engineer's most important and, yes, sometimes most brutal teacher: failure. Because honestly, you learn far more from something that breaks than you ever will from something that works perfectly the first time.
So what happens when you completely misjudge those invisible forces and totally misunderstand how your materials are going to behave? Well, you get one of the most famous engineering disasters in all of history: the Tacoma Narrows Bridge. The culprit behind this disaster was something called aeroelastic flutter. Basically, it's what happens when a steady wind hits a flexible surface and creates this self-reinforcing vibration that can just grow and grow completely out of control. A simple way to think about it is like when you hold a blade of grass between your thumbs and blow across it to make it whistle.
People nicknamed the bridge Galloping Gertie because it would bounce up and down in this really unsettling way, even with just a little wind. It lasted for only 4 months. 4. Then, in November of 1940, a pretty normal 40-mile-per-hour wind turned that gallop into this violent, twisting motion, and the entire structure just ripped itself to pieces.
So, what was the fatal flaw? Well, the design used these solid steel girders along the side, so instead of letting the wind pass through, they caught it like a giant sail. This made it incredibly vulnerable to that aeroelastic flutter, creating a twisting motion the bridge just couldn't handle. It was a really, really brutal lesson in aerodynamics.
But that spectacular failure taught engineers a lesson they would never forget. 10 years later, a new bridge was built on the exact same foundations. They called it Sturdy Gertie, and it uses this deep, open truss design that just lets the wind pass right on through. It is a direct result of learning from disaster, and it's still standing strong to this day.
So when you put it all together, that creative problem-solving cycle, an understanding of all those invisible forces, the unique personalities of materials, and the wisdom you only get from failure, that's when you start to really see the true engineering mindset.
This quote from the book just nails it. The numbers are absolutely essential. You have to be able to quantify the problem. But if you only focus on the numbers, you miss the entire picture. You miss the real-world context where materials fight each other and nature is completely unpredictable.
Which really leaves us with this final thought. Next time you're driving across a bridge, what are you actually trusting? Are you trusting the perfect math on some spreadsheet? Or are you trusting the wisdom of an engineer who knows that materials can fight back, that failure teaches some really hard lessons, and who designs for the messy, imperfect, unpredictable world we all actually live in?
For more explainers that break down the hidden logic of our world, make sure you subscribe to Lazy Reader. We'll help you see the world like an engineer, so you can build it right the first time.